Good evening, friends, and welcome to this GATE Fast Track course. And in this GATE Fast Track course, we are studying strength of materials. And in strength of materials, today we'll be seeing bending stress and shear stress. Okay, so let us start the class. Okay, so we are in the GATE Fast Track course, and welcome to all the participants who are attending the lecture live and those who are seeing the recorded. Warm welcome to them also. Okay, so first of all, last class we have seen shear force and bending moments. Okay, and today we'll be seeing bending stress and shear stress. Okay, so first we will see bending stress, how to find out bending stress from bending moment. Okay, so first we will learn how to find out bending stress from bending moment. Okay, तो उसके लिए we have to see the bending moment equation. Okay, bending stress equation actually. Yes, and what is the bending stress equation? Yes, the bending stress equation is bending stress is equal to the bending moment divided by moment of inertia into y. Now what is this y we will see? Okay, what is this y we will see? First of all, what is this? This is your bending stress, and bending stress is a normal stress. So we'll call this as what? Bending normal stress. Okay. M is the bending moment. In last class we have seen how to find out bending moment. Okay, at any particular section, if I say how to find out bending moment, we'll see today also. Okay. And what is I? I is the moment of inertia. What is I? Moment of inertia. And what is y? Y is the distance from neutral axis. What is y? Y is the distance from neutral axis. Okay. So we'll see the things. Okay, we'll see the things one by one. Let us first focus on what? Let us first focus on the term moment of inertia. How to find out the moment of inertia? Many might be knowing, but many might not be knowing. So assuming that you don't know how to find out the moment of inertia of a rectangle. First, let us see, commonly if you see beams and bars, they will be mostly asking what? Either a rectangle or a circle. Yes. So if we see for a rectangle, okay, if we see for a rectangle, so if you have a rectangle like this, okay, if we have a rectangle like this, see, your rectangle has two axes, right? It will have two axes. One axis is like this, you see, yes, and one axis is like this, yes, one axis is like this, two axes I can say. Yes, I can name this as x-x axis and this as what? Y-y axis, right? And suppose this is the width b. Suppose this is the width b. This is the width b, and this is the depth d. This is the depth d. Okay, this is the depth d, right? If this is the width b and this is the depth d, then if I'm finding the moment of inertia about x-x, it is b d cube by 12. And if I'm finding the moment of inertia about y-y, it is db cube by 12. Yes, this is for a rectangle, right? This is rectangle. Now, if we have a circle, then circle is symmetrical about both axes, right? A circle, if we see, circle is symmetrical about both axes. It is symmetrical about what? Y-y also. It is symmetrical about what? X-x also. Yes. And it has only one dimension, right? It has only one dimension. A rectangle has two dimensions, but a circle has only one dimension. That is what? The diameter. So if we see about x-x or y-y, about both axes, I can say Ixx is equal to Iyy is equal to what? Is equal to pi d to the power 4 by 64. So here I is same about both the axes, right? Here I is same about both the axes. Whereas in a rectangle, it was different, right? BD cube by 12 and DB cube by 12. If nothing is mentioned in the question that which axis, then you should take what? X axis. If nothing is mentioned, then you take what? X axis only. If they mention y axis, then we'll take y axis. Nothing is mentioned, we'll take what? X axis. Yes, and here anyhow both are same, right? Now coming back to the equation. What was the equation of bending stress? Bending stress is equal to my by I. We know how to find out bending moment. Now we know how to find out I. Now what is y? Y is distance from the neutral axis. What does that mean? Let us see. Suppose we have a rectangle like this. So here the centroid is at the center, right? Yes. And this is the neutral axis. This is what? This is the neutral axis, right? This is the neutral axis. It passes through the centroid. So if I'm interested in finding the bending stress at this point, suppose at this point, then I will say what? This is the y distance. So for this point, this is the y. Distance of the point from where? From neutral axis. Suppose I want to find out bending stress here. Then this will be y for this point, right? So for any point, if you see, you should take what? The distance from the neutral axis, and that will give me what? That will give me my y. So y is distance from the neutral axis, right? Yes. Now see here. If we see this equation, bending stress. Now bending stress is what? It is my by I. That means if we keep bending moment and I constant, can I say that bending stress is varying linearly with y, right? Yes. You can see that bending stress varies linearly or directly proportional to y. It is directly proportional to the distance from the neutral axis. Yes. That means I can say bending stress distribution is linear. Is what? Is linear. It is what? It is linear. Yes. That means what? If I plot the distribution of your bending stress, suppose this is the top one, this is the bottom one, right? And this is what? The neutral axis, right? This is the neutral axis, right? So top, bottom, neutral axis. See, at neutral axis, this is the neutral axis. What is neutral axis? It is passing through the centroid. Now at neutral axis, tell me what will be y? Tell me at neutral axis what is y? At neutral axis what will be y? Tell me. At neutral axis what will be y? Tell me. Yes, it will be 0. Yes, y will be 0 here. If y is 0, then bending stress is also 0. Yes, and as you increase the y, the bending stress will increase, and therefore I will get a linear distribution like this, right? I will get a linear distribution of bending stress like this. At neutral axis, bending stress is 0. Yes, and you can see as we move away from the neutral axis, it is what? It is gradually increasing, and it is maximum at the extreme fiber, either top or bottom. It is what? It is maximum in the extreme fiber, either top or bottom. It is 0 at the neutral axis, and other places it is linearly changing, right? It is linearly changing. This is what? This is distribution of bending stress at a particular cross section, right? Distribution of bending stress at a particular cross section. Okay, very good, very nice. Okay. Also, we saw that the sign is different. Means what? Suppose bending is happening. Okay. Suppose bending is happening like this. Okay. So if it is a positive bending moment, then beam is going to be bending like this. So this is what? Positive bending moment, or we call that as what? Sagging. Yes. So I can say this is positive bending moment, or I can say sagging moment, or I can say what? Sagging moment. So in case of positive bending moment or sagging bending moment, I can see that if this is the neutral axis of the beam, then above the neutral axis there is what? There is compression, right? Above the neutral axis there is what? Compression, and below neutral axis there is what? Tension. There is what? Tension. Yes, equation is same. Equation is that only. This is the equation. Equation is this. Here we are talking about it is compression or tension. And if it is hogging bending moment, or I can say negative bending moment, this is what? This is hogging, or I can say this is negative bending moment. In that case, this was the neutral axis. This is the neutral axis, right? So in this case, what will happen? Above the neutral axis, I will get what? I will get tension. I'll get tension, right? And below will get what? Compression. So equation is same, just here it is tension or compression decided by what? It is hanging moment or hogging moment, and also is it below the neutral axis or above? The equation is same, and this is the distribution. And here we saw that we get the maximum value of bending stress. This is the maximum value of bending stress we get at the extreme fiber. We get at the extreme fiber, either at the top or at the bottom, in the extreme fiber, right? Either at top or bottom, extreme fiber. So they are known as what? The extreme fiber stresses. So how to find out the extreme fiber stresses? How to find out the extreme fiber stresses? If I say, if I want to find out the bending stress at the top, right? That will be what? M by I. I will take what? Y top, right? I will take what? Y top. And suppose I want to find out the bending stress at the bottom. See, this B is for what? Bending. It's not for bottom. Huh? This B is for bending. Bending stress, bending stress, bending stress at top, bending stress at bottom. So this will be M Y bottom by I, right? This I by Y bottom, we give a name known as what? Section modulus at top. This is known as what? Section modulus at top. Okay, and this I by Y bottom, this also is a section modulus. This is what? Section modulus at bottom. Section modulus at bottom. Okay. Now what happens in case of a rectangle? Let us see for a rectangle. For a rectangle, what happens? See clearly. For a rectangle, Y top and Y bottom are same, right? Yes. For a rectangle, I can say this is Y top, which is equal to how much? Total depth divided by 2. Yes. And here Y bottom is also what? Total depth divided by 2. So in the case of rectangle, the Z top is equal to Z bottom is equal to I by D by 2, right? Either you take YT or YB. Yes, it is same, right? Either you take YT or YB, it is same. So this is same, and this is what? Suppose I call that as section modulus of rectangle. Yes. And since your Y top and Y bottom are same, and Z top and Z bottom are same, which is by the way how much? I is BD cube by 12 if I take about y xx, and then this is D by 2, I get what? BD square by 6, yes. And since you see Z top and Z bottom are same, right? Z top and Z bottom are same, therefore the extreme fiber stresses also will be same, right? So in this case, in rectangle, the bending stress at top, or you find out the bending stress at bottom, value wise they will be same, right? And what will be the value? M by Z. Yes. How you see? This is actually what? You see, this is M by Z bottom, and here it is what? M by Z top. And since Z is same, so I can take what? M by Z, right? M by Z. Or I can simply take what? M by Z. Z is BD square by 6. So BD square by 6, or I can say 6M by BD square. So this is for what? This is for a rectangle. I can write like this. So in rectangle, the top stress and bottom stress are same. Yes, but they will be opposite in sign. If one is tension, then other one will be compression. And if one is compression, the other one will be tension. It's opposite in sign. But value wise, they are same. Value wise, they are same. If we see for a circle, also, here also y top and y bottom are same. Yes. Yes. Here also y top and y bottom are same. You see, this is here y top is equal to y bottom is equal to D by 2. Same. Yes. So here also if I find out Z top is equal to Z bottom is equal to what? Is equal to, suppose I take how much? I by y top. Suppose you take y top or y bottom same. So this is pi d to the power 4 by 64, and then d by 2, that is how much? Pi d cube by 32. Okay, so here also Z top and Z bottom is same. So here also your top fiber stress and bottom fiber stress will be same, and that will be equal to how much? M by Z only, where Z is how much? It is 32, sorry, pi d cube by 32, right? Pi d cube by 32, or I can say 32 pi m by pi d cube, we can say like this way. So this is for a circle. No need to remember. If you know the things, you can find out in the exam only, right? Next is, see, always y top and y bottom won't be same. Yes, always y top and y bottom won't be same. For example, if you see this, suppose I am drawing a non-symmetrical eye section. If I draw a non-symmetrical eye section, a non-symmetrical eye section will be something like this. Better I draw with hands. The non-symmetrical eye section will be something like this. You see here the bottom flange is more. Right? The bottom flange is more. Okay. Something like this. Okay. So this is a unsymmetrical eye section. So here what will happen? The centroid will be more towards the bottom because more area is here. So centroid will be somewhere here. Right? So what will happen in this case? in this case what will happen? The y bottom will be less, na? The y bottom and y top won't be same. You see, y top and y bottom won't be same. Yes, here you can see that the centroid is more towards the bottom. It's not at the mid height. Yes, it is not at the mid height. Yes, so here y top is not equal to y bottom, and therefore here z top won't be equal to z bottom, and therefore the top stress and the bottom stress will be different. Yes, let us see. You see, the top stress and bottom stress will be different. Yes, how different? You see, the distribution will be something like, it will be bending moment by z bottom, right? And here z top will be how much? Z top will be I by y top. Yes, and z bottom will be equal to I by y bottom. The I is same, but y top and y bottom are not same, right? They are not same. Y top is actually more than y bottom, right? So if y top is more than y bottom, then I can say z top will be less than z bottom, right? You see, denominator na. If yt is more, z top will be less. And if z top is less, then stress is more na. Here you see, you can see that here this is more, because you see denominator. So I can say here bending stress at top is more than bending stress at bottom. They are not equal in magnitude, at least. They are not equal in magnitude, right? But in case of rectangle and circle, they were equal in magnitude, right? They were equal in magnitude. Understood? Chalo, let us solve some questions now, right? So enough of theory. Let us solve some questions now. Big question, huh? So we'll solve so many questions in one question. Normally we do that. Let us read the question. Huh? A simply supported beam carries a uniformly distributed load of 8 kilonewton per meter over a span of 6 meter. Okay. Beam dimensions are 300 into 400 mm. Very good. Find the bending stress. I have 4 questions. Huh? I have 4 questions. First question is depth of 100 mm from top at the mid span. Let us solve them one by one. Nah? Let us solve them one by one. So first of all, it is a simply support beam. Suppose first of all, it's a simply support beam. Yes. Okay. UDL is acting 8 over a span of 6 meter. Eight kilonewton per meter over a span of 6 meter. Very good. Now, what is asked? It is asked depth of 100 mm from top at mid span. First, it is written at mid span and then 100 meter from top. Two information is given. Now, at mid span means what? At center. What is the bending moment? We have seen in previous class, it was WL square by 8, right? For a simply support beam at mid span, the bending moment is how much? WL square by 8. The bending moment is how much? It is 8 into 6 square, 36 by 8. So it is how much? It is 36 kilonewton meter, right? It is the bending moment at the mid span. They have asked the first question is in mid span. So I found out what? WL square upon 8. WL square upon 8. Very good. This is the bending moment we got. Very nice. Next data is given what? Next data is given that we have to find 100 mm from top and beam dimensions are 300 and 400. That means the beam is something like this. The beam is, this cross section is something like this. And I have to find out the bending moment where? I have to find out the bending moment at a point which is 100 mm from top. And what is the beam dimensions given? It is given, you see, 300 into 400 means what? This width is 300 mm and depth is 400 mm. So tell me what is y here? What is y here? Tell me. What is y here? Tell me what is y. What will be the value of y here? Y is the distance from the neutral axis, right? Y is the distance from the neutral axis, right? Y is the distance from the neutral axis. Okay. So this is the neutral axis. This is the neutral axis. So from here, this point, it is written 100 mm from top. So this will be 200, na? Total is 400. Total is 400. So this is 200, right? So this distance is y. And from the diagram, we can clearly see that y is how much? Y is your 200 mm. So game over. What was the bending stress equation? The bending stress equation was, if you see, the bending stress equation was my by I, right? It was my by I, right? Yes. So, see, bending stress you have to find in what? Bending stress you have to find in Newton per mm square. So, everything you put in Newton mm. This is bending moment. This is kilonewton meter. I'll convert into Newton mm. So, kilonewton to Newton, 10 to the power 3, meter to mm, 10 to the power 3, 10 to the power 6. I'm converting everything into Newton mm. So, this is what? 36 into 10 to the power 6 Newton mm. Then y is how much? Y is 100 we got. And what is I? I is BD cube by 12. We'll take about this axis. So, BD cube by 12. This is B and this is D. So, BD cube by 12. So, 300 into 400 cube divided by 12. So, 12 will go here. So, what is the answer you are getting here? Actually, if you see, this is 4 cube. 4 cube means 64 into 10 to the power 6. So, you can do some cancellation. This can cancel, this get cancelled, this get cancelled, this get cancelled, this get cancelled. We get a 4 here and this get cancelled. We get a 16 here, right? So, if we divide by 4, it is 9 and this is 4. So, 9 by 4 is 2.25. Yes. How y is 200? How y is 200? How y is 200? Please tell me, please enlighten me. How y is 200? It is 100 mm from top and beam depth is 400. So neutral axis depth will be, this total is 200 and I am saying 100 mm from top. Okay, so how y is 200? Okay, this is different. ये तो ठीक है. I've used 100 only ना. Here I have might by written. I've used 100 only na. Okay. I've used 100 only na. Understood? So answer is 2.25. Answer is 2.25. Understood? Okay. Next question you do. Next question is what? Depth of, no, I will do. You will take time. Depth of 150 mm from top at a distance of 3 meter from one end. Okay. At a distance of 3 meter from one end. Okay. Distance of 3 meter from 4.5 होगा कैसे भाई? What is 9 by 4? What people are doing here? I don't understand. What is your problem? What is the answer? What is the final answer? 2.25 na? 36 into 10 to the power 6 into y is 100 divided by b d cube divided by 12, it is 2.25. Game over. Okay, why you are wasting time so much? Next question is, next point was what? It was at a depth of 150 mm from top at the distance of 3 meter from one end. So when I write 3 meter from one end, actually it is midspan, na? Yes or no? When I write 3 meter from one end, actually it is midspan, right? Because total is 6 meter. And if I say that 3 meter from one end, so actually we are going where? We are going to midspan. So moment here again will be how much? Midspan moment which we have calculated 36 kilonewton meter. But what is written here? It is written 150 mm from top. 150 mm from top. Okay. 150 mm from top. So what is the y for the second case? Tell me. What is the y for second case? What is the y for second case? What is the y for second case? It is 50. Very good. It is what? It is 50. Because it is written 150 mm from top. And this is the neutral axis. Yes. This total is 200. This total is 200. So 150 from top. 150 from top. So here, right? Here, somewhere here. At this level we can say. Every point actually. So at 150 mm from top. Right? And therefore this will be y. And obviously from here, clearly y is 50. So if y is 50 mm, now we can find out the bending stress. Same equation. I'm writing the value. M y by I. I is what? B d cube divided by 12. How much are getting this? You will be getting 1.125, I think, na? How much are getting this value, this bending stress? 1.125. You're getting this as 1.125 Newton per mm square. Very easy question. Next question, third question. Third part actually. What is the third part given? The third part is depth of 200 mm at the midspan. Can you tell me what will be the answer for 3? Can you tell me what will be the answer for 3? At depth of 200 mm at midspan. What will be the answer for the third part? Yes, it will be 0. Very good. It will be 0. Why? See, midspan given means bending moment will be 36. Bending moment will be 36 kilonewton meter. Very good. But written what? Depth of 200 mm. Depth of what? Depth of 200 mm. So 200 mm depth means what? It is at the neutral axis, na? So at neutral axis, whatever might be bending moment, if the y is 0, your bending stress is 0. If the y is 0, the bending stress is 0. Understood? If the y is 0, bending stress is 0. Even if bending moment is not 0, but y is 0 at neutral axis. Now tell me what will be the answer for fourth part? What will be the answer for fourth part? What will be the answer for fourth part? Again 0. Here what is written? At supports. We know that if we have a simply support beam, we We know that the bending moment is 0 at the supports, right? The bending moment is 0 at the supports. So here you see, here y won't be 0. What is written? At depth of 120 mm. So depth of 120 means y will be 80 here, na? Yes or no? Y will be 80 here. 200 minus 120. So y will be 80, but bending moment is 0. So bending moment is 0 means again bending stress is 0. So you see that point number 3 and point number 4, what happened? Bending moment was 0, so bending stress is 0. Even if y is non-zero, right? And in the third case, what happened? Bending moment was not 0, but y was 0, therefore bending stress is 0. Right? Very good. Right? Now in this first question, first part actually, can somebody tell me this stress which we got in the first one, we got how much? 2.25. It is compressive or tensile? Tell me. It is compressive or tensile? Tell me. It is compressive or tensile? Tell me. It is compressive or tensile? Tell me this stress which we got. It is compressive. Why? I'll tell you. Because you see, if you see the bending moment diagram for a simply support beam, if we see the bending moment diagram for a simply support beam, the bending moment is what? It is all positive, right? Everywhere it is positive. So that bending moment at midspan, which we got, it was what? It is 36 kilonewton. It's a positive bending moment, or we can say sagging bending moment, right? It's a positive bending moment. So when there is positive bending moment, and this point is what? You see, above the neutral axis, right? Yes. So if it is positive bending moment and the point is above neutral axis, then we get what? We get compression. No? Yes. If it is positive bending moment and the point is above neutral axis, we get what? Compression. So therefore this stress is what? This stress which we got, it is what? It is compressive stress. It is what? Compressive stress. So sometimes what happens in the examination, na, they will give like this. They will give 2.25, one option 2.25 compressive, one option they will give 2.25 tensile. So don't get confused. You see, first of all, it is which kind of moment. If it is positive bending moment above neutral axis, compressive, below neutral axis, tensile, right? Because it is sagging, and in hogging the opposite. So remember this, huh? Okay. Let us solve some questions on, so third part and fourth part we solved. Now let us solve some questions on extreme fiber stress. So here what is written, you see another question. They can ask you extreme fiber stresses. This was not extreme fiber, this was in between the beam, right? So these were, I can ask you in between the beam, right? These were in between the beam. So extreme means top or bottom. So if you are interested in finding top and bottom stress, what is written? Simply support beams carrying a uniformly distributed load 10 kN/meter. It also carries a point load at a distance of 2 meters from one support. Very good. Beam dimensions are given. It's a square beam actually. Find the extreme fiber stresses at midspan. So here what to do? You see, extreme fiber stresses at midspan. Here we can't use directly. Why? Because you see the loading is not direct actually. So first of all, you see it is a simply support beam like this. Yes, it is simply support beam. A UDL is acting and then a point load is also acting. But point load is not acting at the center. It is acting at 2 meters from one support. Yes. So point load which is acting is not at the center. It is where? It is 2 meters from one end. And total beam length is 6 meters. So it is not acting at the center. So this is 2 meters, that means this will be 4 meters, right? Because total is 6 meters, right? Yes. And what is the UDL? UDL is 10 kilonewton per meter. UDL is 10 kilonewton per meter. So I have taught you how to find out the reactions, right? So first of all, we have to find out the reactions. Reactions are required, right? Then we can find out bending moment, right? Now due to the UDL, it is 10 into 60. 10 into 660, total length is 6 meters. So 10 into 660. So 60 will get distributed. So due to the UDL, it will be 30-30. Due to UDL, it will be 30-30 distributed, right? Now, due to that point load, we have already discussed how to find out. Due to point load, it will be, reaction here will be, this is, load is how much? Load is 60 kilonewton. So this load is 60 kilonewton. So we have already know how to find out. This is 60 into, this was sort of A and B, na? So 60 into B, 4 divided by what? 6, total length 6. So it is what? 40, right? And here it will be 20, means 60 into, then this 2 divided by 6. So it is what? It is 20. So total is here what? 20. So I can say the reactions are how much? Here it is 70 and here it is 50, right? So the net reactions are what? 70 and 50. So I have taught you earlier also how to find out reactions like this. So you can easily find out this is what? 70 kilonewton. And this is what? This is your 50 kilonewton. Okay, very good. Now I have to find out the extreme fiber stresses, right? You have to find out the extreme fiber stresses at midspan. So for that I need what? I need the bending moment at midspan. Now bending moment at midspan, how to find out? We'll cut a section, right? I have told wherever you want to find out, just cut a section. So I'm cutting a section at the midspan, means what? At 3 meter, right? So if I cut a section at the midspan, so better is to go from left or right? Better is to go from right, because you see right less loads are there, more simple to solve. So if I'm cutting a section, I'm seeing from the right, then I am seeing a reaction of how much? 50 here. Then I'm only seeing a UDL. Yes, and this is 3 meter. So 3 into 10 will give me how much? Will give me a load of how much? 30 actually acting like this, right? At a distance of how much? 1.5 meter. So if I want to find out the moments actually, if I want to find out the moments about this cut section, so this 31 will generate how much? 30 into 1.5. It will generate how much? Like this will generate, like this, 30 into 1.5, 45 kilonewton meter it will generate like this. And this 51 will generate how much? This 51, it will generate 50 into 3, it will generate in this direction. 50 into 3, how much? 150 kilonewton meter. So if I want to find out the net moment generated, the net moment generated will be how much? 150 minus 45. That is how much? The net moment is 150 minus 45, that is 105 kilonewton meter. So on this side, the net moment generated is 105. So to balance this, there will be bending moment of what? 105 here to balance this. So this is what? This is the bending moment we get at the midspan, right? This is the bending moment we get at the midspan. And this is what? This is positive bending moment. You see, this is sagging. You see, this is sagging, na? I've already told. This is sagging actually. This is what? Positive bending moment we have got. So this is the way we find out bending moment. I already taught you in the last class, but again I am telling you. So cut a section, balance the moments. Cut the section, balance the moments, right? Yes. So at midspan we are getting this, what? We are getting this bending moment, right? Now once we get the bending moment, it's over, game over. Once we get the bending moment, the extreme fiber stresses, here the top and bottom stresses will be same, na? Yes. Here the top and bottom stresses will be same because it is what? It is a rectangular section. So it will be what? It will be only 6m by BD square, or m by z basically, right? M by z, right? So m by z, z for rectangle is BD square by 6. We already discussed this. So 6 into 105 into per 6, I convert into what? Newton mm. And width is given how much? It is 400, 400. It's a square beam actually. So 400 into 400 square. Okay. So how much are getting this? What is the bending stress you are getting? Or extreme fiber stresses, right? Top, extreme fiber stresses is asked. So 6 into 105. We can do with our calculator also. Not much difficulty actually. Getting a value of 9 point something, na? How much are getting? 9 point something you should get. 9.844. Okay, I can say 9.84. So see, at top also we will get the same value, at bottom also we will get the same value. But at top it will be what? See, both I will get the same value. But where it will be compressive, where it will be tensile, tell me. Both I will get the same value. Value wise it is same. But where it will be compressive, where it will be tensile, tell me. This extreme fiber stresses. Where it will be compressive, where it will be tensile, tell me. Where it will be compressive, where it will be tensile, tell me. It is sagging moment, right? It is sagging moment. If it is sagging moment or positive bending moment, I have already told. At top we will get what? Compressive. At top we will get what? Compressive. And bottom we will get what? Tensile. Bottom will get tensile. Value will be same because it's rectangle, so top and bottom stresses will be same because y top and y bottom are same. But we will get different values of different nature. One is compressive, one is tensile. Now second part is what you see. So this part we solved. Extreme fiber stresses at mid span. Second is extreme fiber stresses at quarter span. Right? Extreme fiber stresses from quarter span. Let me just add one line here. Quarter span. And I will write here closer to point load. Closer to point load. Because if you see here, there are two quarter spans. The two quarter span things. You see, like you see here, quarter span means L by 4. So L is how much? L is 6. L by 4 means 1.5 meter, right? You can see here, here it is the UDL acting, and then we have this point load acting here. We have the point load acting at 2 meter, right? At 2 meter, this point load of 60 is acting. So actually quarter span means we have two quarter spans. You see this is mid span. You see this is mid span at the center, right? This is the mid span. So if I see quarter span, it can be this also. See, yes, half of this, or it can be here also, right? So what I've written closer to the point load. So we are talking about this quarter span, right? Closer to the point load. So what we will do here, if we want to find out closer to the point load, so what I will do, this is 1.5 meter, na? Quarter span means L by 4, this is 1.5 meter. So I'll cut a section here. I'll cut a section here. So if I cut a section here, then what will happen? You see, this is the reaction. And I'm seeing from this side better, na? So I'm cut a section, I'm seeing from this side. So reaction was how much? Reaction was actually 70 here, right? So 70 kilonewton. And this is 1.5 meter, right? So 1.5 meter and 10. So it will be 15 kilonewton per 15 kilonewton, right? So 10 kilonewton per meter, and it is 1.5 meter. This total is 1.5. So this will be how much? This will be 0.75, right? This will be 0.75 meter, and this will be how much? This will be 1.75 meter, right? Right? And we want to find out the bending moment here. So again, I will balance the moments. And balance the moments. You see, this 15 one will generate how much? 15 into 0.75, right? Yes, it will generate how much? 15 into 0.75. So 15 into 0.75 is given 11.25, right? So this 15 one will generate how much in this direction? You see, and the 71 will generate like this, opposite, right? You see, 70 into 1.5. So I can say it is 105, right? So net moment is how much? Net moment is 105 minus 11.25. So net moment is 93.75 in this direction, right? Like this, right? 93.75 in this direction. So here also 93.75 in this direction. And this is, ladies and gentlemen, what? Your sagging, positive bending moment, right? We have already discussed this, right? So once we find out the bending moment, game over. Once we find out the bending moment, extreme fiber stresses is very easy, right? Once we find out the bending moment, this was part 1. Once we find out the bending moment, then we can easily find out, right? So bending stress at top will be how much? Same equation, 6m by bd square, sorry. So it will be here 93.75 10 to the power 6 divided by bd square. So 400 into 400 square. Little less actually. It is 8.8 around, right? Almost 8.8. And top it will be again compressive. MP I can say Newton per mm square. So that means it is very important we know how to find out bending moment. If we don't know find out bending moment, we cannot find out what? The bending stresses. And to find out bending moment, we should know how to find out reaction. And all these things I have taught before. Okay. So they can ask to bending stress at any location, so that we have seen any depth they can give, or they can find out they can ask you the extreme bending, extreme fiber bending stresses. So this we saw. What else they can ask? Let us see some more questions. You see this question. A structural steel beam has a unsymmetrical eye cross section. Unsymmetrical eye cross section. The overall depth of the beam is 200. The flange stresses at top and bottom are 120 and 80. The depth of the neutral axis, okay, just natural or neutral axis from the top, right? They have asked this question. How to solve this? Very easy. You see here, unsymmetrical means y top and y bottom won't be same. Now see, sigma top is what? Sigma bending stress, this bending stress at top. Bending stress at top will be equal to what? It will be equal to bending moment into y top divided by I, right? And the bending stress at bottom will be what? The bending stress at bottom will be equal to bending moment y bottom by I. Yes. Now see, at a particular section, bending moment will be same, I will be same. So if I take the ratio of, let me just write sigma, means bending stress we are discussing, so I am not writing B. Suppose if I take the stress ratio of bending stress and top and bottom, it is nothing but what? It is the y top by y bottom, right? It is y top by y bottom, right? Other things will get cancelled, bending moment is same, I is same. So here, what is given? The top stress. Top stress is given, at the top it is given 120 and bottom it is given what? 80, right? That means this is what? This is, I can say 3 by 2, or I can say from here y top is equal to 3 by 2 y bottom, or I can say 1.5 y bottom, right? Now see, the total depth is given of the beam 200, right? So it is something like this, you see. It's unsymmetrical eye section, but at top it is more. So y top is actually more here, right? You can see that y top is coming more. So something like this. Oh, sorry. Something like this, you see. It's an unsymmetrical eye section. And here what happened? This is y bottom and this is y top. So we got that, you see, y top and y bottom addition will be how much? It will be total depth, na? Total depth of the beam, which is given 200. Now we know y top we got is 1.5 y bottom. So this plus y bottom is how much? It is equal to 200. So from here I can say it is 2.5 y bottom. So y bottom is what? 200 divided by 2.5. Yes, that is how much? That is equal to 80 mm. So if y bottom is 80 mm, so y top will be how much? It will be 120 mm. And what is asked in the question? In the question this is asked what? The depth of the neutral axis from the top. So depth of the neutral axis from the top. So this is neutral axis. So from the top, so indirectly they have asked what? They have asked what? YT, and YT is how much? YT is 120. Yes. So this kind of questions they can ask from the unsymmetrical I section, right? And easily you can solve. Just you should know this equation, right? That in an unsymmetrical I section, the ratio of bending stress at top and bottom is equal to what? Y top by Y bottom. So this, if you know, you can solve this question, this kind of questions, right? Let us solve another other type of questions which are asked in bending stress. You see what is written? A simply support beam of T section. T section is also what? It's not symmetrical. It's subjected to a uniformly distributed load acting vertically downward. Its neutral axis is located at 25 mm from the top, and total depth of the section is 100 mm. Okay. The ratio of maximum tensile stress to the maximum compressive stress. Now, the ratio of maximum tensile stress and maximum compressive stress. Now see, it is written as a simply supported beam subjected to a uniformly distributed load. If it is subjected to a uniformly distributed load, then the bending moment will be always positive, na? Right? If a simply support beam is there, yes, if a simply support beam is there and it is subjected to what? Uniformly distributed load, the bending moment everywhere is what? Positive only, right? Yes, it everywhere what? Positive only. So if the bending moment is positive, then if the bending moment is positive, then we get the maximum tensile stress where? We get at the bottom, na? Yes, for positive bending moment. And maximum compressive stress we get where? We get the top, na? Yes. So indirectly they have asked what? They have asked the bending stress ratio at bottom, yes, and top. They have not written bottom by top, but because they expect you to find out what? That if the bending moment is positive, then you know, then maximum tensile stress occurs at the bottom and maximum compressive stress occurs at top. So this is what we have seen. This is what? Y top by Y bottom. Sorry. It is Y bottom by Y top. I am having little cough. Sorry. Y bottom by Y top, right? Y bottom by Y top. So you see what is given here. It is given the neutral axis is located at 25 mm from the top and the total depth of the section is 100. That means what? That means the T section. You see, the cross section is T section, something like this, right? The T section, something like this. And the neutral axis is at 25 mm from the top, right? The total depth is 100. Total depth is 100 means what? This will be 75, right? Yes. Total depth of the beam is 100. That means what? This will be 75. So indirectly what happened? This is Y top and this is what? This is Y bottom. This is Y top and this is Y bottom, right? So Y bottom is how much? It is 75 and it is 25. So answer is plane 3. You see, the question is very easy, but there are so many concepts here, right? Its question is very easy. It will take very less time if you know the concepts. If you don't know the concept, it will not be solved. Very difficult. Okay. Next question. What is written? A cantilever beam has a cross section of 300 mm into 400 mm. Okay, very good. Span of 4 meter. Find the maximum UDL which can be applied if the permissible bending stress is 3 MPa. See, whenever they are writing the permissible bending stress, that means what? This is the maximum bending stress, right? That means you cannot cross this, right? So whenever writing permissible bending stress, right? That means what? We are talking about what? The maximum bending stress. Means you cannot cross this. So that means it is telling the maximum bending stress is how much? 3 MPa. Very good. Now it's the rectangular beam. So maximum bending stress occurs at extreme fibers. That means indirectly it is what? Maximum bending stress, which is 3 MPa. Indirectly it is what? It is M by Z. It is what? M by Z, right? Maximum bending stress. Yes, M by Z. Now, what is Z for a rectangular section? It's rectangular section, it is what? BD square by 6. Right? It is BD square by 6. Now, from here we can find out what? The bending moment, right? Let us find out the bending moment here. Very easy. But you have to solve taking care of units. So it is 3 Newton per mm square. This is the maximum bending stress, that is equal to bending moment. So bending moment, let me take in kilonewton meter. So I'll convert into Newton mm by multiplying 10 to the power 6. Then 6 for the BD square thing. And B is how much? 300, 400. Okay, so 300 into 400. So I have taken M in kilonewton meter, so converted into Newton mm by multiplied 10 to the power 6. So what is the bending moment you are getting here? Tell me. How much bending moment we are getting here? The bending moment will be getting 3 into 300 into 400 square, okay, divided by 6 divided by 10 to the power 6. I'm getting 24, right? Bending moment I am getting what? 24 kilonewton meter. So this is the bending moment we are getting. That this maximum bending stress will occur for a maximum bending moment of how much? 24. Now it's a cantilever beam, right? It's a cantilever beam. If it is a cantilever beam, which is having and telling what? It is written having UDL. Having UDL, right? UDL. So it's a cantilever beam and what? UDL. So suppose it is W kilonewton per meter. And this is length. So where we will get the maximum bending moment here? The maximum bending moment we will get at the fixed end, right? At the fixed end, we will get the maximum bending moment, right? So if this is 24, kilonewton per meter, right? Sorry. He'll get the maximum bending moment. Now, how to find out the bending moment? This load will be how much? This load will be W into L, right? Yes. So what is the bending moment generated here? The bending moment generated is W into L, and this distance is what? This distance is L by 2. So this is what? WL square by 2. This is what? This is moment is what? WL square by 2, right? Yes. So the bending moment will be how much here? To balance it, it will be WL square by 2 only. So this is the maximum bending moment here. And this I will equate to his, right? Yes, because if you cut in cross section, then we got how much here at the supports? WL square by 8, and that should be equated to what? Your 24. So this is how much? WL square by 8. So from here you see W I will get in Newton mm. You see from here kilonewton meter, na? So I can take kilonewton per meter. So it will be W is equal to 24 into 2 to 48 divided by L square. L is how much? Length is given how much? Span 4 meter. So L square for 16. 3. Getting how much? 3 kilonewton per meter. Yes. Now, if the same question, if the same question was asked, for a simply supported beam, it was cantilever beam, if the same question was asked for a simply supported beam, then what would have occurred? Here that 24 kilonewton meter you would have equated with what? WL square by 8. Because for a simply supported beam, this is the maximum bending moment, right? Yes. If it was a simply support beam, then I would have equated this to what? I would have equated this to your WL square by 8, right? Yes. So from here, the answer would have been W is equal to 24 into 8 divided by what? Your 16. That is equal to 12 kilonewton per meter. But if it was simply support beam, right? If it was simply support beam. Because cantilever beam, in cantilever the maximum moment will get where? At the fixed, that we found out, WL square by 2, right? So this kind of questions can also be asked in bending stress. Okay. Then something known as radius of curvature. Something known as what? Radius of curvature in case of bending stress. What is that? You see, when a beam bends like this, so actually this forms a part of a what? When a beam bends like this, suppose a beam bends like this or whatever. Okay. So the beam bends like this becomes a part of a very big circle, right? Whose center is somewhere here, suppose, right? When the beam bends, so it becomes a part of a very big circle whose center is somewhere here, right? And it forms a part of it like an arc. So it subtends some angle theta. And suppose that radius is known as what? The radius of curvature, right? And this is the length of the beam. This total is the length of the beam, right? Which bends. So here the length of the beam, right? The length of beam L is equal to what? R theta. Also there is an equation. What equation? The equation is the bending stress by Y is equal to the modulus of elasticity by this radius of curvature is equal to your M by I. This equation known as the equation of pure bending, theory of pure bending by Euler's equations. Okay. So you see, by equating this and this, I got my bending stress equation. What? Bending stress is equal to My by I. And then either I can find out radius in this way if I know the angle, or if I know the bending moment I can find out radius in this way. If I know the bending stress Y, then also I can find out the radius in this way. So in this way we can find out what? The radius of curvature. Let us understand this by questions. Let us understand by these questions. What is written here? Let us solve another question, then I'll come to this question. What is written here? A beam has a same cross section throughout with a length of, with an I, this is I given, with an I of how much? With an I of 10 to the power 8 mm4. Very good. It is subjected to a uniform bending moment. Bending moment also given, right? If the modulus of elasticity is this, what is the radius of the circle into which the beam is bent in the form of an arc? It's very easy, right? You see, I is given, bending moment is given, E is given. Asking what? R. So you can solve question. Which question will use? M by I is equal to E by R. Right? But units we have to take care, right? Units we have to take care. So what I will do, I'll convert everything into Newton mm. That will be better, right? Let us convert everything Newton mm. So E, this M is what? M, I am converting 40 into 10 to the power 6 Newton mm. Okay, so this is Newton mm. Then your I is 10 to the power 8 mm4. Very good. Then E is 2 10 to the power 5 Newton per mm square. Newton per mm square. Very good. And then we have your R. You see, if you see here, Newton gets cancelled. This get cancelled, I get a mm cube here. And then this mm square, this gets cancelled, I get a mm here. And from here, I can find out the R actually in mm. R will be in mm. So R will be how much? You see, this get cancelled into the power 2. So R you will get actually 2 into 10 to the power 7 divided by 40, right? This much mm. If I want to find in meter, then I have to divide by 10 to the power 3, right? So this much meter. $500 meter, right? Getting R equal to how much? 500 meter. Yes, I'm getting 500 meter. You see, so this kind of questions, very simple question they can ask you, right? Very simple question you can ask you from this equation. M by I is equal to E by R, right? They can ask you from the other equation also, a bending stress. Which one? You see here. See this question, a thin steel ruler, a scale kind of thing, cross section of 0.0625 into 2.5 centimeter is bent by a couple means a moment, applied to the end so that the length L equals to 25 centimeter. Okay. When bent as a circular arc, subtend a central angle of 60 degree. Okay. If the modulus of elasticity is this much, the maximum stress induced in the ruler. So let us solve this question. How to solve, I will tell you. See, actually the ruler means what? The scale which you use for measurements. Actually it is kind of a flat beam, right? Something like this. Yes, something like this, right? Yes, and you sometimes play with that in your childhood. The length is given how much? Length is given 25 centimeter. Now see, the depth is given how much? The depth is given, this is the depth, right? Normally ruler has a thickness, this is the thickness, right? 0.0625, and normally this is the width, right? You see, this is the width, 2.5, right? 2.5 centimeter. So if you see the cross section of ruler is like this here, right? The cross section of ruler is like this, you see, 0.0625, it is the depth actually. It is the depth, and width is what? Width is your 2.5 centimeter. Now you will say that, sir, actually the depth is always more and the width is less. But for a ruler, actually, if you see a ruler or a scale, for that actually the depth, the thickness is less, right? The width is more actually, right? So it is something like this, right? And length is this much, right? Very good. They have asked the maximum stress induced. Now how to find out that? Very easy. We'll use this equation. What? Sigma by y is equal to your E by R. Now see, if I want to find out the maximum stress, then I would take the maximum y, right? And for a rectangular section, yes, the maximum y is what? Depth by 2, na? For a rectangular section, the maximum y is what? The depth by 2. In this case, the depth is actually the thickness. So actually it is what? 0.0625 centimeter by 2, right? Yes or no? If you see, in this case, the maximum bending stress will occur at D by 2, right? Extreme fiber, I can say here. Something like this, right? So, maximum stress they are asking. So, I will use Y max as this. Very good. E I know. E I know. This is centimeter. This much I got. E I know. Okay, is given in the question. Now, what I need is R. What I need is R in centimeter, if I can find out. Now, how to find out R? Very easy. I have already told. If the scale is bent, so I can say this is the length of the scale, which is 25 centimeter. Now it forms the arc length, right? And I can find out the radius. How? Because the angle subtended is given. The angle subtended is given how much? It is given 60 degree. 60 degree means in radian it will be how much? It will be pi by 3, right? 60 degree in radian is what? Pi by 3. So I can say your L is equal to R theta, or I can say R is equal to L by theta, or I can say 25 centimeter by theta, but theta I'll use in radian actually, right? So how much centimeter are getting R? If we put this, how much you're getting in R? 25 divided by pi, 25 divided by pi into 3, then I am getting 23.87, right? I am getting R as how much? 23.87 centimeter, right? 23.87 centimeter. So now I can put and find out the maximum. I can use this equation now. Yes, I can find out the maximum bending stress. Sigma max is equal to E 2 into power 5 6 kg per centimeter square. Then Y max we got is 0.0625 by 2, na? This is Y max. And then R will divide. So R is 23.87. This is in centimeter, this is in centimeter. So both centimeter will get cancelled, and I'll get the answer in kg per centimeter square. Let us find out how much I'm getting. 2618, right? Yes, 2618.35. So 2618.35 kg per centimeter square. Very easy. So you can see this kind of questions they can ask you on bending stress. We try to solve many kind of questions in your bending stress, related to bending stress. Okay. Next we'll go to shear stress. So next we'll go to what? Shear stress. So many types of questions on bending stress we solved. Let us go to shear stress. Now how to find out the shear stress in a beam? The equation is, if you want to find out the shear stress, so shear stress equation is due to shear force. Obviously this is what? Due to shear force. Due to torsion we will see tomorrow. Okay, due to torsion also there is shear stress. We have already discussed, right? But that we'll see tomorrow. To torsion thing we'll see tomorrow. Due to shear force, suppose B, the shear stress equation is B A y bar divided by IB. What is this? This will understand with respect to rectangle. Then we can apply to other things also. So in rectangle, this is the neutral axis. Suppose I am interested in finding the stress here, right? And B is the shear force, I is the moment of inertia. So B and I are clear. B is the width of the section. So width of the section is anyhow constant in rectangle, right? If I want to find out here at this level the shear stress, anyhow this is what? Here B only. So B is the width of the section. Now what is A? A is this area. A is what? A is this area. Area above the point. Area above the point where shear stress is determined. Where what? Shear stress is determined. This is what? This is your A. Understood? Above the point where shear stress is determined. Now what is y bar? You see this area A, you take that centroid and the centroid of that area from the neutral axis. It is what? Y bar. So I can say y bar is that. What is y bar? Y bar is distance of centroid of A from neutral axis. So this is what? This is your y bar. Okay, very good, very nice. Okay, now we'll apply this for a rectangle. Okay, let us apply this for a rectangle. Okay, so if we apply this for a rectangle, suppose I am interested in finding the shear stress at a level here. Suppose any level, suppose this level, which is at y distance from the neutral axis. If this distance is y, you see this distance is y. Now see this rectangle dimensions will be what? This rectangle dimension will be, this will be equal to actually d by 2 minus y, na, you see. This will be d by 2 minus y, right? If this is y, then this will be d by 2 minus y, right? And this is your width, right? So this area, this is the area A, yes. So if I am interested in finding at this level, so this will be the area which is a rectangle. That area A will be how much? The area A will be this width into the depth. Yes, and depth is how much? The depth is actually d by 2 minus y, right? Now if I am interested in find out y bar was what? The distance of centroid of this area from the neutral axis. This is y bar, right? This is y bar. Now how to find out y bar? Very easy. You see this is the centroid, right? This is the centroid. This is the centroid means this distance will be how much? This distance will be, you see, this distance will be d by 2 minus y divided by 2, right? So this will be d by 2 minus y divided by 2, right? This distance, you see. this distance, d by 2 minus y divided by 2. And this is anyhow what? Y. If this is y, so I can say what will be y bar? Y bar will be equal to, see, d by 2 minus y divided by 2 plus y, right? D by 2 minus y by 2 plus y. Now if I just take this as common, so this will become what? You see, d by 2 minus y plus y divided by 2 plus 2y divided by 2. That gives me what? That gives me d by 2 plus y by 2, right? Yes, d by 2 plus y by 2. This is your y bar, and that is your a, and this is your y bar, right? So now if I am interested in finding out the shear stress, so what is shear stress? Shear stress is V A y bar, V A I y bar by I B. That is equal to, V is V, A is what? What we got? A, d by 2 minus y, yes, into B, right? This was A, right? This was A, right? Yes. Yes. And what is y bar? Y bar we got how much? We got y bar as d by 2 plus y divided by 2. So I can say this as d by 2 plus y divided by 2. Yes. So A y bar, then divide by what? I into B. So what happens? You see, B gets cancelled here, right? And then you see this is d by 2 minus y, d by 2 plus y. So this becomes what? This becomes, you see, V d square by 4 minus y square, yes, and then divided by what? 2i, right? Then divided by what? 2i. Now if I simplify it little further, yes, if I simplify little further, one second, correct, yes. If I, oh, let me not simplify, let me write down this only. So this we got as what? The shear stress is what? V by 4i, you see, d square by 4 minus what? Y square. You see, that means what? You see, it is varying, shear stress is varying with what? Y square. So shear stress is varying with y square means what? The distribution is what here? Parabolic. So the shear stress distribution is what? Parabolic due to shear stress. Whereas bending stress was linear, right? Bending stress was linear, but it is what? Parabolic, right? It is parabolic. So if I am interested in finding out, the maximum one, okay. So see, at y is equal to d by 2, means what? Y will be d by 2 where? Top and bottom, na, you see. See this is y, na. So here y will be what? D by 2, here y will be d by 2. So at top and bottom I can say, okay, at top and bottom I can say y is equal to d by 2. If you put y is equal to d by 2, that will become what? D square by 4. Shear stress will become 0. So shear stress is 0 at top and bottom in case of your rectangular cross section. Yes, whereas if you remember in bending stress was 0 at neutral axis, whereas here it is 0 at top and bottom, right? And where you will get the maximum? So shear stress is equal to maximum shear stress when at y is equal to 0. So when y becomes 0, you see, it is minus y square. So y is 0 means what? Minimum value. Then what will happen? That will be maximum, and that will get the maximum shear stress. So maximum shear stress is what? V by I, then d square by 4. Now see, this is V, d square by 4. Now what is I? I is BD cube by 12, na? If you see, it is BD cube by 12, na? Some mistake I have done somewhere. Somewhere I have done some mistake. Let me just check. By 2 plus y. Oh, yes. That's what I was telling. 2y. It was 2y. Yes. But still some mistake somewhere. If it is 2y, then also some mistake we have done. Let me see from starting. VA y bar by IB, very good. Y, yes. Then D by 2 minus Y, very good. D by 2 minus Y by 2 plus Y, very good. Y bar is equal to D by 2 minus Y plus 2Y by 2. So D by 2 plus Y by 2. Very good. A is B into D by 2 minus Y bar is not correct here. Sorry. Y bar is not correct. Okay, we have done correct. We have done correct. No problems. Okay, so here we got, you see, B by 2y, D square by 4 minus Y square. And then what I did, then at y is equal to 0, we get this value. Then I just put the value of I. So it is B by 2i, BD cube by 12, right? And then D square by 4. This gets cancelled, 6 and then 3 and then 2. And this get cancelled, I get V by BD. So that means I got the maximum shear stress. How much? 3 by 2 of BD. Now you see, this maximum shear stress we get at what? At the center. This is how much? 3 by 2 by V by BD. So this is what sort of? Total shear force by total area. So this becomes what? Average shear stress. So this becomes what? Average shear stress. Right? Yes. So therefore, if I see a rectangular cross section, in this case, what happens? If I get a rectangular cross section, then what happens? If I see the rectangular cross section, then what happens? I can say the shear stress distribution. Yes. If I see the rectangular cross section, then the shear stress distribution is something like this. At top and bottom, you're getting what? 0. Yes, we're getting what? 0. And then we are getting a parabolic distribution, right? Then we're getting a parabolic distribution, and we will be getting the maximum at the neutral axis. So at neutral axis or the mid depth, we'll get the maximum one. and this maximum shear stress is what? It is 1.5 times of the average shear stress. And what is average shear stress? The total shear force by total area. Very easy. So this was shear stress distribution. You see, bending stress distribution was little different, right? Yes. If you the bending stress distribution, it was linear. That was parabolic. This was linear, right? And here you see, at neutral axis, we are getting bending stress actually 0 here. Yes. Here we are getting the maximum one. And here we were getting the maximum bending stress at the extreme top and bottom, right? Here we are getting the maximum one, right? But here actually we are getting shear stress as what? 0 here. So here I have highlighted the difference between shear stress distribution and then bending stress distribution, right? This we understood. This was for rectangular cross section. Now for circular cross section, I am not deriving, I'll directly give the conclusions. Okay, I can derive also, but not required. Okay, we have to do in a little fast manner. Derivation is not required. Derivation was just for your what? Understanding for the rectangle. For circle also you can, if you want to derive, you can derive, but anyhow you have to remember the conclusions. So in the circular section, what happens? In a circular section, again we'll get the same. At top and bottom you will get 0 shear stress. Again you will get a parabolic distribution, right? Again you will get a parabolic distribution, and you will get the maximum at neutral axis only, or mid depth, right? Maximum shear stress. And here the maximum shear stress is equal to 4/3 times of the average shear stress. And what is the average shear stress here? The average shear stress will be how much? It will be the shear force divided by the area. Area is what? It's a circular area, right? So pi/4 d square. Okay, now see what happens in a circular section. The maximum shear stress occurs at the, this is the neutral axis, this is also the mid depth, right? This is the neutral axis, this is also the mid depth. Okay, so I can say for a circular cross section, the maximum shear stress occurs at the neutral axis, and that is what? The mid depth. Yes, so these three are same actually. And same I can tell for what? For a rectangular also. Here the maximum shear stress occurs at the neutral axis only, right? And this is what? The mid depth also. Right? But that is not the case for a triangular section. For a triangular section, the things are little different, and we should know that. They ask questions, we'll solve questions also. For a triangular section, these things are little different. How? For a triangular section, if I am interested in finding the shear stress, then here the maximum shear stress occurs at the mid only, but here the mid is not the neutral axis, right? You see, if you see, this is like this is the top, this is the bottom, this is the bottom, okay, and this is the mid depth. Let me draw the mid depth a little bit later. Top, bottom, mid depth, right? Neutral axis. Neutral axis is different, right? Neutral axis is different from mid depth. In triangular section, neutral axis is different from mid depth, right? Yes. So I can say, if you see, this is the total depth divided by 2, whereas this is the neutral axis, right? This is the neutral axis. So this neutral axis is at what depth? It is 2d/3, right? It is 2d/3, right? Because in a triangular section, centroid passes through d/3 from the base, or 2d/3 from the top. So this is the neutral axis, and this is the mid depth. So here what happened, if you are drawing the shear stress distribution, then again you will get 0 at top and bottom, right? Again you will get a parabolic distribution. Again also will get a parabolic distribution, but here maximum shear stress you will get at the mid depth only. Yes, but this is actually mid depth, but here it is not what? It is not equal to the shear stress at the neutral axis. Here shear stress at neutral axis is different, you can see, right? it is different. The neutral axis is not same as mid depth, and obviously it is less. And this maximum one is your 1.5 times of average one. Yes, and neutral axis one is 4/3 of average one, right? And average one is what? It is a triangular section, so average one will be V by BD by 2, because for a triangle area is what? This is D and this is B. So area is what? It is actually BD by 2, right? Yes. So if I am interested in finding for a triangle the maximum shear stress, actually it is what? 1.5 times of V by BD by 2, right? Yes. 1.5 times of average. So it is actually 3 by 2 BD by 2. So get cancelled. I can say what? 3V by BD, right? Whereas if I want to find out at neutral axis is what? Actually it is 4/3 of V by BD by 2, that is equal to 8V by 3BD. 8V by 3BD. Understood? This is for triangle, right? This is for triangle. This is for a triangle, right? If I say for a rectangle, the maximum shear stress actually is equal to what? Shear stress at neutral axis. That is equal to 3/2 times of V by BD, right? Understood everyone? All these small things, difference between a triangle, rectangle and a circle. They ask these three sections a lot, so we will focus on that only. So questions time. Okay, questions time. This is how you revise fast, right? Yes. So a rectangular beam 300 mm into 400 mm rectangle is subjected to a shear force. Find the maximum shear stress in section. Also find the percentage and change in the maximum shear stress. If same, it will not same stress, it should be same shear force is applied on a circular section of diameter 300. First, for the rectangle one, you find out the maximum shear stress. Okay, shear force is given 200 kilonewton. You find out the maximum shear stress for the rectangular section. How much it is? Tell me. For a rectangular section, what is the maximum shear stress you are getting? Tell me. (1.5 times of BD, right? (2.5 na? 2.5 you are getting, right? So for a rectangular section, it is 2.5 Newton per mm square. Now same if you are applying for a circular section, then maximum shear stress is what? It is 4/3 times of average. Means 4/3 times of shear force is same. So I'll take the same shear force divided by area. 300 mm. So how much you are getting this maximum shear stress for circular section? Because it is what? 4/3 times of your V by pi by 4 d square, average shear stress. So for circular section, how much you are getting? Sorry, this is for rectangular section, this is for circular section. How much you are getting? 200 into 1000 divided by 300 square divided by pi. 3.77. Oh, sorry, 3.77 na? Huh? 3.773 Newton per mm square. Okay. So if it is rectangular section, I am getting 2.5. If it is circular section, I am getting how much? 3.773, right? So what is asked? The percentage change. What is the percentage change? The percentage change will be, it is changed to how much? 3.773 from 2.5. So original is 2.5 into 100. So 3.773 minus 2.5 divided by 2.5 into 100. I'm getting 50.92, right? So almost 51%, right? Almost 51% increase, I can say, right? Almost 51% increase. So you see, one question we understood many concepts, right? Almost 51 percentage change. So this kind of questions they can ask. Let us solve another question. A rectangular beam. This question you try first. This question you try. First you try this question. Then I'll solve. First you try this question. A rectangular beam of width is given and shear force is given. Permissible shear stress means what? Maximum shear stress, right? Permissible shear stress means maximum shear stress is given. They're asking you the depth of the beam. Very simple, straightforward question. Please solve this question. Solved. 266 something. Let us see. So 2.25 MPa maximum shear stress is what? This is rectangular, right? Rectangular means 3 by 2 of B upon BD, right? So this is equal to 3. Don't forget to convert the units. Don't forget to convert units. So 150 10 to the power 3 convert to Newton. Then 2, B is how much? B is given 250 and we have to find out D. So very easy, from here you can find out D. I'm not calculating. People are telling 266.7. Na? Let me take 266.7. Others also getting the same value? No, 400 we are getting, right? No. We're getting 400. Let me check. I'm getting 400. I'm getting 400. Check what mistake you did. We'll get 400. Hmm? 400 will get. You see, if you calculate without a calculator also 3, 5, right? This is 500, right? And then 100, right? So 300. So D is equal to, I can say, 900 by 2.25. So this is actually 400, na? 400. With the calculator also we can calculate 400, right? 400. Yes. हाँ तो permissible is maximum shear stress, right? Yes. Yes. So maximum shear stress, the permissible one, which is 2.25, that is equal to 3 by 2 of V by BD. Understood? Understood? Yes. Okay. Next question. This is another kind of question. What is given? A cantilever beam of this much width, this much depth, and this much span is subjected to a UDL of A kilonewton per meter. Okay. It is subjected to a UDL of A kilonewton per meter. Very good. If the permissible stress is 1.25, find A. It's a rectangle. The rectangle, right? Permissible means maximum shear stress. So it is given, the maximum shear stress is given as 1.25 MPa or Newton per mm square. So what we will do first, we'll find out the shear force, the shear force corresponding to this. So how we'll find out? Maximum shear stress is 3/2 V upon BD is equal to 1.25, right? So 3/2, this B is actually in kilonewtons, so I'll convert into Newton. So B is how much? 300 and 400, right? So from here I can find out V. How much is B? I am getting 1.25 into 300 into 400 into 2 divided by 1000 divided by 3. B I am getting 100, right? B I am getting as 100 kilonewton. B I getting 100 kilonewton. Okay? So this is 100 kilonewton. Now that means for this much shear force, we are getting this maximum shear stress. Now in a cantilever beam, where we get the maximum shear force? Sorry. For cantilever beam, where we get the maximum shear force? We get at this support, na? How much? You see, this is A and suppose the length is L. So this whole force will be how much? A into L. So here I will get balancing shear force of how much? V into L, right? Sorry, A into L, sorry. So here indirectly what happened? This maximum shear force which I am getting, A into L is equal to how much? 100 kilonewton. And A will be how much? 100 kilonewton divided by L. L is given how much? 4 meter. A is 25 kilonewton per meter. Understood everyone? Everyone understood? Understood how we solve this question? Very easy question. You remember a similar question we solved for bending stress, right? Right? There what we were doing, we were finding the maximum bending stress m by z, and then we're equating to what? At support the WL square by 2. Remember? Similar here, shear force. Section. Something will solve from triangular section also. So triangular section. A triangular section of base 300 height is subjected to a shear force of 200. Find maximum shear stress. Maximum shear stress we get where? At the mid one, right? And that is how much? 3/2. 3/2 of average. And average was what? It was BD by 2, right? Because in a triangle the area is BD by 2, right? Yes. So here 3/2. Yes, 3/2 into V. V is what? 200 into 10 to the power 3 divided by what? Divided by BD by 2. So B is how much? B is 300 and D is 200. Now divided by 2, right? Very easy. This is base is 300 and height is this, right? So I can easily find out 2 get cancelled, this gets cancelled, this gets cancelled. Easy. So 10, na? Maximum stress is 10, na? Yes. So maximum stress is 10, I think. 10 Newton per mm square. Now the next is what? Next is shear stress at neutral axis. I had told, what I have told? I have told that shear stress at neutral axis for a triangular section is not the maximum one, right? So this is how much? This is 4/3. then average shear stress. So B by BD by 2. Now students get confused. Now I'll tell you. Students get confused. They get confused that that maximum one occurs at midspan. Okay, very good. For a triangle at least, for a triangular section. Yes. For a triangular section, maximum one will get at midspan. Yes. And then for neutral axis, okay. Students get confused that where it is 1.5, where it is 4 by 3. Students get confused. Where it is very easy, you see now. See, this is 3 by 2. 3 by 2 is what? 1.5, na? And this is 4 by 3. It is what? 1.33. Obviously, this is maximum, na? So it has to be 1.5, na? Yes or no? Obviously, it is maximum. So it will be 1.5, and 1.33 obviously will be less than 1.5, right? So don't get confused that which one is which one. Obviously, this is maximum one, and maximum one should be 1.5, because 1.33 is obviously less than what? 1.5. So then here you can use average stress B by, don't forget, BD by 2, because triangle, and then B by BD by 2. Game over. So if I find out here, 4 by 3, B is 200 into 10 to the power 3 divided by your 300 into 200 divided by 2. So I can solve this again and get cancelled. How much are getting this? 8.89. Okay. 8.9. And obviously we'll get little lesser value, right? Obviously we'll get little lesser value. Yes. Okay. We'll get what? A lesser value. Okay. Like in childhood, now we have studied. Okay. In childhood we have studied. Okay. In childhood where others were studying, we might be sleeping, na? So in childhood we have studied, right? That in triangle, the area is what? BD by 2. But some people were sleeping that time in childhood where teacher was teaching, so they were sleeping. Okay. So in childhood we have known this. When we're very child. But okay. And in ultra childhood we have also studied that that this is BD by 2. But again we have forgotten that. And then we aim that we have to get into top 80 and all. Okay, good. Understood? Next, this question. Okay, this is little complicated, right? So let us study this. I think this is the last question. Last question. So many things are there here. Let us read the question carefully. A rectangular section of span 6 meter. Let us write all the data. Length is 6 meter. Width is 300 mm. Depth is 400 mm. Is subjected to UDL of 8. Okay. Okay. Nothing is mentioned. Nothing is mentioned. We can assume simply supported. Huh? Find the shear stress at 75 mm from the top at the distance of 2 meter from the supports. Let us solve the first question. Huh? See, the first question, it is written what? This is the beam. Total is 6 meter. Okay. Okay. At 2 meter, they have asked, right? 2 meter from the support. 2 meter from the support. 2 meter from the support, we have to find out what? The shear force, right? You have to find out the shear force. So now UDL is given 8 kilonewton per meter and it is 6 meter actually, sorry. So reaction will be how much? 6 into 8, 48. So 48 divided by 2, 24, right? 48 divided by 2, 24. So reaction is what? Reaction is 24 kilonewton. Reaction is what? 24 kilonewton. 8 into 6, 48. 48 divided by 2, right? Very good. Now, we have to find out the section at 2 meter. Why? Because they're asking you the things at distance of what? 2 meter from support. So this is 24. And this UDL is 8. So this is 8. What total force here? At 2 meter, 8 into 2, 16. Very good. So what is the shear force? To balance this, the shear force will be how much? 8 kilonewton. Shear force is how much? 8 kilonewton. Yes, I have already taught you how to find out shear force and bending moment at any point. Cut a section, cut the section, balance the forces. Game over. 8. And it is positive, na? It is positive shear force. Because you see, section right hand side, it is down. So it is positive shear force. Okay. So shear force we got. Now what is that? Shear stress at a depth of 75 from top, 300 and 400. You see, what is the meaning of this? Depth is 400, width is 300, right? Very good. So this is 300, this is 400, right? And they're asking you to find out the shear force where? At this point. How much? 75 mm from top. If this is 75 mm from top, yes, then this is how much? This is 125 mm, right? This is 125 mm. Very good. Very good. Now you have to find out the shear stress here. At this level, you have to find out the shear stress 75 mm from top. What to do? Either you can use the equation I derived or directly you can use this equation. Which equation you see? You can use shear stress is equal to which equation I told? VAY bar by IB. I can use this equation. How? Very simple. You see, shear force we got. Shear force was what? 8 kilonewton. So 8 into 10 to the power 3 because I converted into what? Newton. Okay. Area was this area, na? You see, area is this area, na? Because I told wherever you are finding, take above that. So this area is how much? You see, this area is 300 into 75, na? You see, 375. This area is 300 into 75. Whatever I will write down, what is I? BD cube by 12. B D cube upon 12. So 12 will go up. What is B? B is 300. Very good. Now remains Y bar. Y bar was what? Y bar was, you take the centroid of this and this distance from the neutral axis. So you see this is 75. So this will be 37.5, right? This 37.5 and this is how much? This is your 62.5, right? Sorry, 125, right? So I can say, what is Y bar from here? I can say the Y bar is 125 plus 30, 155, 162.5 mm, right? It is how much? It is 162.5 mm. Khatam, finish. And so I'll just put the values and find out the shear stress now. Very easy. You can use this equation, you can easily find out. Very easy. So how much are you getting? Tell me, let us find. I will also calculate. You also calculate. 8 into 10 to the power 3 into 300 into 75 into 12 into 162.5 divided by 300 divided by 400 cube further divided by 300. Wait, some calculation mistake I did. Point 0.06 I am getting, na? I'm getting 0.06. How much you are getting? 0.061, yes. 0.061 Newton per mm square. Let me just cross check the values once. Let me just cross check the values. 8 kilonewton meter, 48, 24, 24, 24 minus 16, 8, yes, 8. 8 into power 3, yes. Or if you want to use the equation, na, remember we derived the equation. What was the equation? V by 2I d square by 4 minus y square. Now this is applicable for only rectangular cross section. That equation is applicable for all section. This we derived for rectangle, right? So if we derive for rectangle and use this, V was what? 8 into power 3, then 2I 300 into 400 cube by 12. D is how much? 400. So 400 square by 4. Y. See, Y is how much here? Y is this one, na? Yes, this is Y, 125. So if you put this equation, are we getting the same value? Let us see. 400 whole square divided by 4 minus 125 square into 12 into 8 into 1000 divided by 2 divided by 300 divided by 400 cube. I am getting the same value. Yes, I am getting the same value. Yes. So better, if you don't want to remember this equation, not required. There is no requirement to remember this equation, right? There is no requirement to remember this equation. You can use this equation and you can easily find out, right? If you know, it is more easier to, you can easily remember. There is no requirement to, remember additional equations, because you see, this is applicable for rectangle, but this is applicable for any cross section, right? It is applicable for any cross section. So any cross section they give, you can apply this equation and get the same answer. Okay. So better to not remember more equations, right? That equation I derived just to prove that the stress is what? Parabolic. Otherwise, there is no need of this equation. There is no need of this equation. If you want to remember, you can remember. You can always solve the question by using this equation also. Let us solve the next question. Shear stresses at depth of 100 mm from top at midspan. So this is very easy actually. What will be the answer of the second one? What will be the answer to the second question? What is the answer to the second question? Please tell me. It is 0, big 0. Midspan. Yes. Midspan means shear force is 0, right? We know that. Okay. We know that for a UDL, yes, and simply support beam, okay, right? This is the shear force distribution, and at midspan the shear force is 0. Shear force is 0. So shear stress, whatever might be A, whatever might be Y bar, whatever might be I, whatever might be B, will be 0, right? Because here B is 0. So from top to bottom it will be 0 only, right? At midspan. So wherever shear force is 0, similarly when bending moment was 0, bending stress was 0, right? So irrespective of wherever depth you are seeing, right? Very good then, thank you very much. That's the end of the lecture. So we studied bending stress, right? Today's lecture was aim was what? To teach you how to find out bending stress and shear stress. Okay. So first you should know the governing equations, right? The governing equations was what? Bending stress by Y is equal to E by R. They can ask you questions from E by R also. We have solved, right? So using these equations, we can find out bending stress anywhere, and also we can find out extreme fiber stresses, right? So so many questions we solved for bending stresses, right? And shear stress, what was the governing equation? VA Y bar by IB, right? And we also saw the distributions, also saw for rectangular sections, many things we saw. I think most of the things are covered. Sorry. So tomorrow we are going to study what?